we turn to present a MATLAB demo for this topic of dictionary learning. We start with a synthetic experiment in which we compare the dictionary learning algorithms we have just presented. Our experiment starts with the creation of a random dictionary D of size 30 by 60 elements with normalized columns. We synthesize 4,000 training signals by creating random sparse vectors of length 60. Each such vector contains 4 non-zeros in random locations and having random values. These are multiplied by D and noise is added. The obtained set is the training data for the algorithms we are about to test. The training makes use of the knowledge that the cardinality of the representations is 4, and the resulting estimated D hat is then compared to the original one. We explore the behavior of the MOD, the KSVD, and the speeded up version of them. In the sparse coding stage, we use the OMP, forcing each representation to have 4 non-zeros. The algorithms are evaluated by checking the per sample representation error, which should be 0.1 or below, since this is the additive noise level. Another measure of success is the distance between D and its estimated version. How do we evaluate the distance between D and D hat? This is done by sweeping through each of the true atoms and seeking their match in the estimated dictionary. Such a match is counted if the inner product between the two is above 0.99 in absolute value. This threshold was chosen so as to guarantee that the atoms found are far cleaner than the signals we have trained on. In order to show this, let's change notations and denote these two atoms as U and V, where V is a noisy version of U. The question we pose now is how strong this noise could be if we require an inner product of 0.99 and above. The analysis presented below is simple, showing that the level of noise we permit in the atoms is 15 times weaker compared to the noise in the signals. It starts with an evaluation of the squared L2 distance between the two, being the noise power times the vector length. The same expression, when opened, leads to a lower bound of 0.02 since the two atoms are normalized and since we have a limit on their inner product. The conclusion is clear. Our requirement is quite strict, so if indeed met, it means that we truly found the original atoms to a high level of accuracy. Good, so let's run this demo. This is the file demo1 synthetic that will accompany us in this part. In the first part, we generate the dictionary and the data just as described above. Notice that the signal-to-noise ratio of the training signals has been computed and it stands on about 20. In the second part, we run the learning algorithms. We set few parameters and then turn to run the MOD, the KSVD, and the speeded up method. All are activated from the function trainDic, which we will not dive into. You are more than welcome to take a look at it by yourself offline. As we run this code, you will observe that the program outputs the average residual in each iteration, and it is descending nicely. We also present the accuracy of the found dictionary, and this measure grows quite fast towards a 90% recovery and beyond in all algorithms. The third part in the code presents the results graphically. Figure 1 shows the percentage of recovered atoms as a function of the iterations. As can be seen, all algorithms are quite successful, with a small edge to KSVD and more so to its faster version. Figure 2 shows the residual error, and here the success of all algorithms becomes quite evident. After 15 iterations and even less, all methods achieve an error of less than 0.1, implying that the found dictionary is just as good as the best possible result, since we assign 4 non-zeros per each example, while representing it to within an average error that is smaller from the true noise power. This concludes this part of the demo. We proceed by presenting the dictionary learning process on image patches. We extract all the 8x8 overlapping patches from the image Barbara and choose 10% of them at random. These are 25,000 patches that will serve the training process. We initialize the training using the redundant 2D separable DCT with 121 atoms and compare the MOD, the KSVD, and their speeded up version. In all these runs, we apply 50 iterations and a fixed cardinality of 4 in the representations. In this test, we cannot compare the found dictionary to the true one since there is no reference to compare against. Our test thus relies on the generalization error obtained on the rest 90% of the patches, which the training part has not seen. Let's run this demo. We show now the file demo2 patches. The first part of this code gathers the patches to train and test on, all extracted from the image Barbara. The second part computes and presents the redundant 2D DCT that will serve as the initialization to all the learning algorithms. We turn to the third part in which we run the 3 training methods just as before. Now there is no reference dictionary to compare with, and thus our evaluations show only the average residual. This error is clearly descending in all 3 algorithms. If you observe more closely and experiment with this code by yourself, you will recognize that the MOD runs faster than the KSVD, and these two are faster than the accelerated method. The reason for the noticeable differences is the relatively small number of training examples we use, and the very effective pursuit algorithm employed called batch OMP. When a group of signals go through a pursuit together, all using the same dictionary, various speed-up tricks can be used. Batch OMP employs such shortcuts, thus substantially reducing the runtime of the sparse coding stage. We present the resulting dictionaries, and as can be seen, they do capture the texture that is so typical to the image Barbara, along with various edge atoms. Part 4 of this code creates a graph that shows the training representation error as a function of the iterations. As expected, the fast method is fast, and MOD and KSVD follow closely. We also show the 3 resulting dictionaries. They look similar, but it is hard to assess whether they are identical or even close to each other. We will come back to this matter. The 5th part in the code evaluates the generalization over the entire set of patches, training and testing together. The representation errors clearly show that the trained dictionaries are far better than the initial DCT and that the KSVD is slightly better than MOD. The last part of the code checks whether the dictionaries obtained from the MOD and the KSVD are close by. Using the same metric we defined earlier in the synthetic case, we get that there is an overlap of only 15% between the two. This suggests that the space of feasible solutions is quite rich.